Kelly, please.
Hello, everyone. Welcome to today's edition of our chemical metrology seminar. Thanks for joining us. Our speaker today is Supratik Guha of the University of Chicago at Argonne National Lab. He'll be speaking on a very relevant topic in today's current state of the world. He'll be talking about aerosol filtration efficiency in various cloths and masks. So over the past couple months, we've had several different speakers in our seminar series, a few from the world of metrology and various other research scientists. So Professor Guha, as I mentioned, is from the University of Chicago from the School of Molecular Engineering. He's also a scientist at Argonne National Lab. Before joining the University of Chicago, he was a research scientist with IBM and the director of physical sciences there. His research expertise is in semiconductor and oxide materials and devices for information processing technologies. Before joining IBM, he was a senior material scientist at 3M for a few years, and this was after receiving his PhD from the University of Southern California. And Professor Guha, I will pass things over to you.
Great. Thank you very much, Kelly. And thank you, Zoltan, for giving me the opportunity to present this talk. So can you guys see my screen?
Yes, we can.
Okay, I'm going to do slide share. Okay. Okay, great. So thank you. And I am very happy to give this talk today. We'll talk about what we've done. My name is Supratik Guha. I am not a respiratory test specialist. I'm a material scientist. I work on semiconductor materials and materials for quantum information processing, sensing. So you can think of materials for information processing in general. With the labs shut, this is some work that we did in the month of April, using some special permissions to open up some labs and do some experiments. And I'll come to it in a moment. And with that, let me begin. Hold on, I need to, okay. So can you guys see the first slide? I just changed the slide. It should show a couple of pictures.
It's good.
Yes.
Okay, good. So masks, facial coverings have come a long way. If you look at the picture on your left, this is what doctors used to wear during the plagues in Europe in the 18th and also parts of the 17th century. Doctors would go visit their patients using long beak-like structures. And these beaks were, like you can see, were stuffed with things like lavender, various herbs, etc. And the theory in those days was that it would prevent the miasma from entering. So they felt that these diseases were transmitted by something called a miasma, and this was obviously before the germ theory was discovered or presented. And then, of course, in the eye sockets, they would have glasses covering it, they would gowns. So they knew that these kinds of things transmitted through the air and probably touch. Now, we've come a long way since then. And on the right, I'm just showing you some examples of disposable masks that we're using today. But with this pandemic and with almost all governments and organizations recommending the use of masks, cloth masks have become widely prevalent, particularly in the US. And indeed, the World Health Organization 2 days ago came out with the first sort of technical specification for cloth masks, which is a very good thing. On the next slide, I'd like to point out a National Academy, the US National Academy of Sciences report that had come out last year on respirators. and it was prescient in many ways. And this one talked about elastomeric respirators. So most of you must have seen these. These are the ones that give you a really nice seal across the face, etc. And we'll talk about that soon. But basically, I'm highlighting a couple of things here that says, given recent concerns about pandemics and emergent diseases, reusable respirators are recommended. And then they go on to say that people should stockpile these reusable respirators. Now, that did not happen, unfortunately, but this is where we are. So now let's turn to the issue of cloth masks. I mentioned to you that they're being increasingly used. And, late March, early April, we realized there was very little data on the filtration efficiencies of cloth masks. So we wanted to do these measurements quickly using, instruments that we had. We wanted to see the performance of the different fabrics. And also things like, what we realized going through was the effect of gaps and their importance. This is the fit of the masks. Now, the SARS-CoV-2 virus is roughly about 100 nanometers in size. When people breathe or cough or speak, there are aerosols generated in dimensions roughly from about 10 nanometers and higher. And the aerosol range, which is about 10 nanometers to 10 microns, is the size range that hangs in the air. The larger ones fall due to gravity quicker, the smaller ones hang around. Given that the COVID is, hold on a second, please. I seem to have lost my screen. Can you guys see the screen again?
Yeah,
Yes, we have.
Yeah. Okay. So the virus appears fairly large, but it's not known right now what size droplets are going to be critical for transmitting COVID. It appears that if the droplets are very small, then they're not going to be even large enough to have much of a viral load. I'm not an expert in this subject, obviously, but it also seems like nobody clearly knows what exactly this viral load is expected to be. But the belief is that this is transmitted in a respiratory way, when through breathing, through speaking, through coughing, through sneezing, and that's where the 6-foot rule and all of that comes in. So now this is something we learned. There's a lot understood about the filtration of droplets or particles by filtration media. So the very large particles will come, they will hit a fiber cross section, and then they will fall to the ground due to gravity. The mid-sized particles will have their momentum appreciably distorted by the gas streamline, and that's the picture at the bottom middle. And then they can be intercepted by fiber cross sections or things. And then the finest particles can be retained electrostatically. For instance, those effects. Let me just put it this way: the electrostatic effects become more important for finer particles with smaller masses that are then held by charge transfer processes. So that's what's in a nutshell what is known about the different processes by which droplets and particles get stuck in a filtration media. Now, we tested a whole bunch of cloths, common cloths, materials, and their specifics are given in our paper and listed over here. We were not textile people, we were not mask people, and so we were not textile people, and a lot of this stuff we did not specify in the way the textile folks do, and there's a lot of confusing terminology there as well. But we tried to cover a bunch of different materials that people use. Here is the experimental setup. It was very simple. We wanted to do very quick experiments and put the data out as soon as possible, because at that time there was really very little data. People were not paying any attention to the kind of cotton that they were using. Many people would wear sort of loose, holey cotton, or very stretchy stuff, knit stuff, and just did not seem to be their awareness. So we wanted to make some relative measurements. Okay, that was key for us. So it's a tube, as you can see in the middle, and across the tube we have a cloth sample mounted with a hose clamp. And then we suck on the receiver end of the tube, which is on the left, with an exhaust fan. We introduce air from the chamber on the right. We mix the aerosol. The aerosol is created using a sodium chloride particle generator. This is a standard process thing used in mask testing. Our fan blows the aerosol, and then we measure the particle distribution upstream and downstream using a combination of two instruments, both made by TSI. The optical particle sizer, which depends upon an optical scattering technique, and that measures particles, roughly from the 300 nanometer and upwards in size. We measured from between 300 to 6,000 nanometers, so 6 microns. And on the other side, on the nanoscan, we measured particles with 300 nanometer or less dimension. That was a separate instrument, because the OPS is not very good in those smaller dimensions. Typically, the OPS is much higher sensitivity. The nanoscan can measure in the smaller range, but it has a lower sensitivity. But we were interested essentially in getting histograms, the filtration as a function of size. So one important thing to note, and this is what happens when you write paper quickly and try to put it out there, is in the paper, the flow rates that we published is in error, and errata has been submitted, and hopefully it should appear soon. We submitted it last week. In the paper, we noted that flow rates were used of 1.2 and 3.2 cubic feet per minute. These are typical rates for resting and sort of moderate respiration rates. Now, these were measured under unrestricted conditions, meaning there was nothing covering the mouth of the tube when we measured these flow rates. So it was under, basically zero resistance, near zero resistance flow. Now, when you put a cloth filter on, the flow rate drops, and that flow rate can drop by an order of magnitude or more. So this correction has, please note this, we've sent this, and again, it should appear, I hope, soon. So when we did our measurements, we therefore did our measurements at very low flow rates. And at that point, the measurements represent close to what I would say are diffusion limited conditions. Now, this is what we do. As I said, we measure particles upstream. We take the histogram, and then the figures on the top left and top right represent that, measured with the nanoscan and the OPS. And then we measure the counts downstream, and we take the ratio, and that gives the filtration efficiency. We did at least 6 measurements used to calculate a weighted average, etc. All those details are there in our paper. Now, our measurements were carried out typically at pretty low pressures. There was about a 2.5 to 13 Pascal differential pressure across the cloths. Most of our results were measured at 2.5 Pascals. We focused, and I'll come to this more in detail later, we focused on the low pressure differential range, because in real life cloth masks, because of leaks around the sides, it is going to be difficult, we believe, to sustain high pressure drops. Okay, so more on this later. Now, analyzing concentrations, we did some test runs with N95 masks and surgical masks, and they behave as expected. There are big error bars on the 300 nanometer and less size because of the sensitivity of the instrument. So this data should be interpreted within the limits of the error bars. And again, a word of caution, N95s, fitted respirators, are tested by ASTM under very different conditions, much higher flow rates, much higher pressure drops. Because the traditional N95 testing, which has gone on for decades, was for a different purpose. Fitted respirators for use, say when you're woodworking and you got sawdust coming, etc., etc. And as I'll talk later, we need to ask, what is this cloth mask protection for? But anyway, our measurements, as I mentioned, were carried out under far different conditions, so no direct comparisons should be made. Now, different fabrics, these are the kinds of results we got. We got, certain fabrics behaved very poorly, certain fabrics behaved very well. And we found a few general things here, that there are two kinds of filtration that one should consider, the mechanical filtration and the electrostatic filtration. And materials like silk, for instance, are known to have very strong electrostatic properties. And so their electrostatic filtration properties can be leveraged. We found that the weave and the tightness of the threads matter a lot. Look at the picture on the top, for instance. If we took an 80 thread count cotton, which is the green, it performed poorly. On the other hand, if we did a 600 thread count cotton, it performed very well. An old cotton quilt performed very well. Now, keep in mind, these are at very different flow rates, right? And the flow rates would be different for the 80 thread count cotton than the 600 thread count cotton. But we also found that hybrids worked well, and we believe that if you combine electrostatic filtration along with mechanical filtration, that might be the best approach. In a sense, multi-layers might be a good approach of going about this. It was interesting to look at the role of leakage. What we did is we measured our mask with just the mask covering the tube, and then we measured it by opening up two small 1/4-inch holes just on the side of the tube next to where the mask was mounted on the rim. And there's dramatic differences in the efficiencies, as you can see in the figure below, both for surgical masks as well as a cotton and silk hybrid. And this is a known thing to respiratory specialists. They were not surprised. But to many of us who are new to this area of using masks, this was a big revealer, right? That you get a lot of leakage around the gaps of the mask that fit your face. So this is just a rough summary of our various filtration efficiencies that we've seen. The pressure differential is around 2.5 pascals. Keep in mind that the flow rates are not the same for all of these. They vary between each other. There's been, since then, so there had been a few works on the measurement of filtration efficiencies of common fabrics. And since our paper, a lot more has appeared, and they have been measurements of different types. These papers are appearing almost every day. So I haven't had an opportunity to thoroughly read every one of them so that I know all the details. But there have been many innovative ways of looking at it. I think people are starting to try to understand where can these cloth masks be useful. But there are wide variations in efficiencies. Some of us measure very high efficiencies, including us, for various types of cottons and hybrids. Some of us measure very low efficiencies. You can see Zhao et al.'s paper that came out recently in nanoletters. A lot of this, I believe, has to do with the conditions of the measurements and the pressure differentials and the flows. Many measurements have been done not by pumping air through a mask, but by saying, hey, I'm going to try to simulate in real life, what is the protection when someone is speaking or talking, and so they spray an aerosol, and then they put this mask on a Petri dish, and then they let stuff go in through the Petri dish, and then they measure what came out the other side, either using microbiology type experiments or by looking at some kind of fluorescent counting. So there's been different innovative approaches for this, but this, as far as I know, is sort of the latest in the efficiency measurements of various cloth fabrics. The key outcomes from our study were that A, tight weaves are better than open weaves. I think this was one of the biggest, things we wanted to point that, look, don't go for knit masks or, open masks or, pay attention, or t-shirt cotton. The tighter the weave, the better it is as a filter. Use multi-layers, probably a combining electrostatic and mechanical filtration may be a good thing. And then thirdly, the fit is critical. That the gaps between the face and the mask is very important. And our measurements were carried out at the low pressure differential range, which we think is very important and relevant for cloth masks. So let me come to that. So what is it about cloth mask design that is different? What are the uses and considerations we should look at here? So if you look at N95 masks, they are typically fitted, right? Some of the N99 masks have elastomeric fits. N95s also have fits. And their testing, as I mentioned, is very rigorous. Now, cloth masks, it's all kinds. They're not standardized. They're not rigorously tested, and the fit isn't great. Right? And so, what happens if we look at the figure on the right? I've drawn this arc, the blue arc, that represents a mask. So there is air passing through the mask, and there's air also passing through the leakage in the mask. Now the flow rate through any media, it's like the Ohm's law. It's the pressure differential on either side of the media. Think of the media like a resistor. It's the pressure differential divided by the resistance. Okay, and the resistance is area dependent on the media. Now, if you have two different pathways, you can think of it like the little electrical circuit on the top where these two resistors are in parallel. So in a real life cloth mask, you will have these two different pathways through the media and through the gaps. And the gaps dominate in real life. And because of this, the pressure differential P1 minus P2 will not be too high. Right? What is it? I haven't seen any clear measurements of this pressure differential yet, but there's something that maybe we can learn from what people have measured in N95 and surgical masks under real life conditions. Now, an N95 mask is typically tested at the pressure differential of somewhere around 300 pascals or so, okay, roughly. Now, in real life, people have tested fitted N95 masks, and the pressure differentials in real life are somewhere between 20 and 50 pascals. And these are fitted N95s, okay? And unfitted, you know, casual user wearing N95, it's probably more near the lower range. Now, there's been one study that I've seen where people have looked at surgical masks and the pressure differential, and they measure it anywhere from between 1 Pascal to about 18 Pascal using mannequins. So it seems likely that the pressure differential for cloth masks is probably somewhere in that range, right? So the low pressure range where sort of diffusion limited transport through the membrane, that becomes important. Now, if the pressure differential is low, you know, cloth typically has a higher resistance. They're not engineered like N95 materials. The flow rate is going to be low. So in most cloth masks, if you want to increase the flow rate, you compromise the resistance, you compromise the, you know, the filtration properties of the mask. And if you go for a better filter, then you get more leakage through the sides. You'll get significant leakage in all cases, so you got to optimize where you want that conductance to be. Which brings to the question of where do people use cloth masks? What are they useful for? And these are all, you know, there's no consensus on this yet, right? So traditionally, N95s and all have been tested for inward protection. You know, I'm a woodworker and I'm working in an industrial place, and there's diesel fumes, and I want to protect myself from this stuff. For cloth masks, we're looking at inward and outward protection. And in fact, many people believe, and there's good reason to believe, that cloth masks really provide strong outward protection. So there's these two things, right? There's inward and outward protection. And then there's the matter of forward protection. Is it more important? So if I'm following the 6-foot rule and I'm speaking with someone, sure, I'll have some stuff leak out from the sides, but is it more important for me at that point to have forward protection? And to that, there's a very nice paper on ARCS IV that was published very recently, and that's the square at the bottom left, where they've carried out experimental studies of these masks. And if you look at the picture on the right, they look at, you know, I believe this was an image taken during speaking. I think it was speaking, not coughing, where, you know, without a mask, that's kind of what, you know, the aerosol output, you know, flow pattern looks like. What they found was that using cloth masks, obviously, you know, N95s work the best, but using cloth masks, the front filtration, depending on the type of cloth, could be reduced by about 90% or more, okay? And multi-layers work better, consistent with the results that we observed. And of course, if you use cloth masks, then you get more jets, because the air has to come out somewhere, the aerosols have to come out. You get more stuff coming out through the sides. So this brings to the question, oh, look, if I'm speaking with you and, you know, we're wearing masks, probably forward protection is critical at that point. And so this is where the cloth masks, I think, are offering a lot of help. And this is where increasing the resistance, increasing the filtration properties will really help. But keep in mind that regular cloth masks, there's a lot of leakage around the edges. Okay, I think we can't go around that. Now, one way to try to minimize that and get the best of everything may be to rethink cloth mask designs. We're kind of stuck too much in the way we think about these N95s and so on. And that is to increase the area of the mask itself. So if you're looking at two resistors, R1 and R2, if the resistivity is high, I can reduce the net resistance by increasing the area. Okay, I'm just circuit way, I'm just adding more resistors in parallel. So if I could make a mask with, say, 10 times more area, so if I could make a mask, let's say roughly, what would it be? About, 400 or 500 centimeters square, or maybe even 300 centimeters square area. I could have a low pressure drop, but I could have much higher flow rates, and the effect of the perimeter, the seal perimeter, as long as I can keep that constant, could be minimized. So I think there's lots of opportunities for cloth mask designs, trying to increase their effective area 10x. Now, this has to be done in an aesthetic way so that it doesn't look ugly. In fact, people do something like this in HVAC areas where you must have seen pleated filters. That's the purpose of a pleated filter, to get more surface area. But I think there are very interesting sort of aesthetic ways of trying to do that. So I just contacted a colleague of mine who's a scientist, but she's also a fashion designer, and she's looking into that. So I think these design considerations become very important for cloth masks. What we've tried to do is provide some very quick data on what is the filtration properties of different cloth materials. And with that, I will end my talk, and I'm happy to take questions.
Thank you for that interesting talk. So first I'll open it up to those in the Zoom call, if anyone in our group has any questions.
Thank you very much, Supratik. Very interesting presentation. I have a quick question regarding the N95 pressure drop, or the pressure test, or the pressure regime, and the pressure regime is what you were using in your studies. Is it fair to summarize that the overall filtration capacity is entirely driven by the fit? So the actual material of the filtration material is of secondary importance? Because you mentioned that even with the N95, the routine fit is 1/10 of the pressure than the test regime.
Yeah. So the test regimes are, possibly done with elastomers and so on. And, this is one, yes, this is one paper, or maybe a couple of papers have reported this in the 20 to 50 Pascal regime. So in real life, yes, the fit can strongly determine the overall effectiveness. I would not say that this makes the filtration media itself irrelevant. I think both are relevant. One thing I'm learning talking to, I got into this by collaborating with a couple of respiratory test specialists at Argonne. They are the ones who did the measurements. And they are not surprised by this at all, because, they do this sort of fit testing. And what they told me is that even if you have like a 5 o'clock shadow, a day's beard, it will compromise. So these guys are obsessed with the fit of the respirator. And if it doesn't fit well, then really it doesn't work well. That's why, for instance, you must have seen those respirators with elastomeric fits. Those are, N99 types. Those really fit well. They have a good seal, etc., etc.
Yes, thank you. Thank you very much. Very interesting.
Okay, so I have another question somewhat related to that. You mentioned all the different types of cloth masks you can have. And just from personal experience, I know when you go online, there's so many different designs that you can use. And one big difference between them that stands out to me is a sort of surgical style mask where it's just one piece of cloth or maybe pleated, or a mask that has a seam down the middle. So if you ignore the fit and leaks through the sides, that seam down the middle where this needle's going through while it's being stitched, is that something you tested, or is that something you maybe speak to how you think those holes would make a big difference?
Yeah, no, we did not test that specifically, but I would doubt that those holes would make a big difference. They're very small. They got thread running through it, so I think it should be okay if you scale to the overall area of the mask.
That's good to know. Thank you.
Yeah, but I'm kind of, we're learning as we're going forward, and I'm kind of thinking that where cloth masks really offer protection is this front protection when talking to people, when facing them, talking to them, and also outward protection. So what happens is when I'm speaking, right, when I'm breathing, let's say when I'm speaking, a lot of aerosol droplets are coming out. And what happens is that when these droplets come out, they aerosolize further and shrink in size, right? And then they become smaller droplets. And then those guys can go into somebody's respiratory passages. If I'm wearing a cloth mask, I can intercept the big droplets coming out. I mean, they're still aerosol particles, but let's say they are several microns. I can intercept them and prevent them from going outward and then aerosolizing into smaller particles, because once they aerosolize into smaller particles, they're hanging in the air for much longer, okay? The bigger particles will fall due to gravity. So I think that's one of the things that's happening. And the second thing, as I said, is the forward protection. I think those are the two things where they are really helping. Again, there is no clear proof for it, right? But this is the picture, at least to me, that is emerging.
Okay, thank you. And is there any other questions in our Zoom call here?
Yeah, hi, can you hear me? It's Ralph. I have a question.
Yeah, I
can hear you, Ralph.
Okay, great. I'm curious, on the first few slides where you're looking at the efficiency for filtration or capture of particles of various diameters going through your filters, there seems to be a continuous decline in filtration efficiency. But there is a point at which around 150 nanometers, there seems to be a marked discontinuity. And I'm wondering, what is the reason for that? Has anyone speculated about that?
Yes, so, so it is well known that around 300 nanometers, actually somewhere between 100 and 300 nanometers, is the size range that is the most difficult to filter, because those particles are too large to be caught electrostatically, and they are too small to be caught by, impaction or interception.
Okay.
So it's well known that there's a window there. Now, I don't know if our data, I think it's catching that window, but I'm not totally sure, because, our error bars with the less than 300 nanometer measured with the other tool are large, right? So if you take that into account, sometimes the interpretation can be fuzzy.
Thank you, and thank you for a great lecture. Very interesting.
Welcome.
Okay, anything else?
I have one more question if we have another minute. I'm just wondering, looking at one of your first slides with the ancient, the plague era face masks or face covers, these long beak type face covers. Why we are not using any of those designs these days? Because not beaks, but some kind of design where the filtration or the sedimentation of the particles would not happen in 2D through a cloth layer, but through a tube, like a snorkel type design. Or this is just engineering, is not practical.
Yeah, I think if you could do a long, like a snorkel or something, and then you pleat the sides heavily, I think you could really increase the surface area, right? And if you really increase the surface area, then you can minimize the effect of the gaps on the face and get the benefit of everything.
That's what I was coming from. Yes, yes.
Right. The problem is, it's probably not going to be, an aesthetic design, right? So I think that's where the challenge is. For instance, in the old days, Western women used to wear this veil-like thing, falling from the rim of their hat, right? If people wore something like that with the face seal, those could be great masks. But again, those are probably not practical. So this is kind of the challenge. Can somebody think of clever designs that people would like to wear, which will give you this surface area?
Thank you. Thank you very much.
So we actually just had a couple of questions pop up on the live stream. We've had a few minutes to answer those.
Yeah, I have time. Yeah.
Wonderful, thank you. First, do you think it would be advisable to standardize the methodology to test these cloth masks?
Yeah, I think so. I think it'll take some time, because I think a lot of people are testing cloth masks the way they look at, ASTM or NIOSH testing of respirators. And there's a difference between fitted respirators and cloth masks, and there's a difference in purpose. And maybe we should be practical about cloth masks and say, look, realistically, this is the kind of protection you're looking at. I may be wrong, but but my feeling is that unless somebody figures out some very clever way of putting seals on cloth masks that the general public can, that's idiot proof, let's say, there's no point doing tests on high pressure differentials across a cloth mask. Because if I can do that, I would go get N95 material anyway. Yes, there's a global shortage today, but that's not because those materials are difficult to make or they are too expensive. People will have those materials pretty soon. And I think that shortage will be met. So if you're going to use cloth masks, you're probably looking at a different type of design here. So I think the World Health Organization has, coming back to your question, and as I mentioned, has come out with the first sort of guidance on cloth masks, and that's a great starting point because somebody needed to do that. There are some issues with that guidance. If you look at the technical details, they give pressure as pascals per centimeter square. I have no idea what that means. Maybe it is some technical, respirator term that I don't understand, because the units are off. But it's a start, right? And this will create debate. And then from these types of documents, eventually there will be a regulated document that will come up from the government. And this is how all these specifications get standardized. So I totally agree this needs to happen. People are coming at it from different directions. And so hopefully it'll all get resolved.
And did you do any examination of whether washing changed the efficiency of the filtration materials?
Not in any great detail, but that's another excellent point. It needs to be checked out, right? If we want to look at cloth masks, sort of, does it have a future? I would say that it could have a future if you can think of, washable, multiply usable cloth masks that can replace one-time disposables, and that these are masks that can then be locally sourced. But I think the washability angle needs to be figured out.
And then related to that would be, a lot of designs are suggesting putting things like coffee filters or vacuum filters in a pocket in the mask. Did you take a look at anything like that?
No, we didn't take a look at coffee filters. We thought about vacuum filters, but then we found that, vacuum filters, a lot of them have asbestos and, maybe not asbestos, but other fibers in them that may not be the best thing to put next to your nose. So we just didn't do it.
Okay, and then finally would be, do you know which of the filtration mechanisms is more dominant? Is it the physical filtration, electrostatic filtration?
In our studies, I think because we are measuring under very low flow rates, low delta P's, we're measuring, I would say, up to 1/10 or even more of the respiratory measurement needs, right? We're probably looking at the diffusion limited regime where things are not coming in with a lot of momentum, but that's my feeling. Now, the question is, if I have a cloth mask, it's got a low pressure across it, right? That's kind of the static situation. Now I speak, I'm not really on any reasonable time scale building up higher pressure, but maybe I'm building up instantaneous higher pressure. And how that physics works out, what the delta P is all unclear right now. But there'll be instantaneous dynamic pressure rises, but in a cloth mask, you're not going to be able to sustain that.
Okay, thank you very much once again. And so if there's no further questions, just thank you, Professor Guha, for taking the time to come and speak with us today about this very relevant and interesting topic.
Great. Thank you very much for inviting me again. Kelly, Zoltan, thanks again for the invite.
Thank you very much for coming, and for our YouTube followers and audience to tune in, and see you in the coming weeks. Thank you very much, Professor Guha. Goodbye.
Take care. Bye.
Thank you. Bye.
Bye.